All right, we're going to quickly review some basic graphs. So the graph that we have here is a linear equation. We know that because it is in the form y equals mx plus b, we call that the slope-intercept form, where b is our y-intercept and m is our slope. And just a reminder, slope is our change in our y's over our change in our x's. You also might have learned that as rise over the run of the graph. So for this, I'm going to draw my x and y axes. And I'm going to start with the y-intercept of -2. That means I'm going to go to -2 on the y-axis and put my point. So that's y equals -2. Now the slope in this case is 3. So we can call that 3 over 1, which means from this point, -2, I go up 3 and over 1 to the point 1, 1. Now that allows me to draw my line. Now, if you'll notice, looking at this, we can conclude that for our domain, remember the domain is all the x values for the function, we can conclude that there is not a single x value that will not work as an input into this. In fact, we can say that the domain is -infinity to infinity. That's what these arrows would mean at the ends of our graph. We're saying that they continue on. Likewise, we can say for our range that it goes from -infinity to infinity because it goes down as far as -infinity and up to positive infinity. We also have other graphs. The next one that we're going to look at is a very simple basic graph again to graph, but the domain in. All right, so if you remember, this is the graph of y equals x squared. It's a parabola passing through the point 0, 0, opens up. We know that the value for 1 and -1 will be the same because whenever we square a number, it becomes positive. So now looking at this, we have to ask ourselves, what is the domain and the range? Well, it's very obvious from the graph that the domain extends from -infinity to infinity because every x value, it goes on and on forever this way and on forever this way. However, for our range, we are limited. If you notice, this graph never goes below this point or this height on the y-axis of 0. So for this, we actually are going to use a bracket instead of parentheses, and we're going to say that it starts at 0 and it includes 0, and it goes all the way up to positive infinity. Let me just erase that there so that you guys see that that is a bracket. All right, so again, it can include 0 and it goes up to infinity, but it cannot go below 0. All right, for a problem like this, when we just need to know the domain of a function, we do not always need to graph it. Usually to find the range, one of the best and easiest ways to do it is to graph it and get the overall picture. But for domain, because we're dealing with the inputs, we just have to simply ask ourselves, is there a problem with an x value? In other words, would an x value get me an answer that does not exist? We are doing this in the real plane, so we do not want to have imaginary numbers. I notice that this has a square root. So we simply need whatever is underneath the square root to be greater than or equal to 0. It is okay to square root 0, so we can include 0. Well, this is a simple inequality that I can solve by adding 1 to both sides and then interpret this as the domain is 1 and including 1, which is why I have the brackets, all the way up to infinity. Now, if I'd asked you to find the range, I know by looking at this what my range is going to be. My range is going to be 0 to infinity. Now, maybe you're having a problem understanding where that range is coming from. I know that the square root function, the basic square root of x graph, looks something like this. Well, I know using my transformations that this -1 inside of the function has shifted it to the right one. But it has not actually changed any of the heights of the graph. It's only shifted it to the right. So my heights stay the same. So this will still start at a height of 0 and continue on to a height of infinity. And that's how I know the range. Now, this question didn't ask for that, but that would be a quick and easy way for you to determine that. Looking at this function, I do not actually see when it's time to find the domain for this one, I don't see any square roots. So I'm not worried about having any imaginary numbers. What I am concerned about is that I cannot divide by 0. And since this is a rational function, we have to make sure that the denominator does not equal 0. So I don't even care that this numerator is 3. As long as it's a constant or a polynomial without square roots, we're good, which a polynomial wouldn't have square roots, so we're good. So looking at this, as long as that's a polynomial in the numerator, we're good. I'm just worried about the denominator and what would make it equal to 0. So I need to know what values of x are going to make this equal to 0. And if you remember back to your Algebra 1 classes, a lot of times we would factor out this x. So I just factored an x out of both terms. And then I recognize that in order to get 0 as a product of two factors, one of the factors must equal 0. So this one's obvious. The obvious case would be x could equal 0. And the second case would be, well, if x equals 1, this would equal 0. And as long as one of the factors equals 0, their product will equal 0. Now to interpret this as a domain, so if I go ahead and interpret this as a domain, this means all real numbers work except for these two. So it means I can start at negative infinity, I can go up to 0, but I cannot include 0. And then my next interval will start at 0 but not include 0. It'll go to 1. And my last interval will start at 1 and it can go up to infinity. What we do is we put a union symbol between these three subintervals to indicate that all of them make up the domain. Again, it's very important that you have the parentheses around the zeros and the ones because you are saying that they are excluded by doing so. All right, now we're going to take a look at the difference quotient. And we've already dealt with the difference quotient, and this one in particular that we're going to start with looks very familiar. In fact, if you notice, if we looked at this as the 2 points, x, f of x, and a, f of a, then to find the slope between those 2 points, it would actually be this equation. F of x minus f of a, those are my difference in my y values, and x minus a. So this is just another slope equation. Now, one of the reasons that we like the difference quotient is that it allows us to find multiple slopes without having to repeat the process. For instance, if I wanted to know the slope between the point 1, 2 and several other points, so if I had the point 1, 2, and I wanted to know the rate of change or the difference in the rate of change between 2 points, say the point 5, and in order to find the corresponding y value on that, I would simply take 5 plus 3, which is 8, divided by 5 plus 1, which is 6, so it would be 4 thirds is what it would reduce to. So we have the point 1, 2 and the point 5 and 4 thirds. If I want to know the slope between those two, I can use my traditional slope formula, which is, in this case, it would be 2 minus 4 thirds over 1 minus 5. And I'd be able to figure out what that slope is. In fact, let's go ahead and do that. So if you remember from algebra, and even just your basic fractions, we need to find an LCD in the numerator. Well, the LCD would be 3. So we would have 6 minus 4 over 3, and then 1 minus 5 is negative 4. All right, so now looking at this, the numerator would become 2 thirds, and my denominator is still negative 4. Well, if I take 2 thirds and divide it by negative 4, that's the same as multiplying by negative 1 fourth. Then I'm able to reduce, and I end up with negative 1 sixth. So the slope between those 2 points is negative 1 sixth. Now, if I wanted to find the slope between, say, the point 1, 2 and the x or value of 10 and its corresponding y value, I would have to repeat this process and do all the simplification. Well, instead of doing that, if we find a generic formula for the rate of change between 1, 2, and any of the other points, then I can just plug in those corresponding x values, and that will always give me that slope between those 2 points. Okay, so we are going to go ahead and make a generic equation that will find the slope between the point 1, 2, and any other point on this curve. So in other words, we're going to find the slope of secant lines that all contain the point 1, 2. Now, how do I know it's the point 1, 2? Well, I know that it's the point 1, comma f of 1, because in functional notation I know that's how they go together. Well, to find f of 1, on the previous slide I just did it by looking at the graph and found the corresponding y value. But for this case, let's say I don't have the graph. All I need to do is plug 1 into this original equation, and I would get 1 plus 3, which is 4, over 1 plus 1, which is 2, and that's going to reduce to 2. And that's how I know that f of 1 equals 2. Okay, so I'm just going to follow this formula right here. Now, f of x, I'm going to substitute f of x with what f of x value is, which happens to be x plus 3 over x plus 1. Then I'm going to subtract from that what I just found for f of 1. Well, f of 1 we found was 2. So I'm going to subtract 2. Now, all of that is over x minus 1. And the most common thing to do is forget, because you already have a fraction in there, you forget to keep it all over x minus 1. All right, just like in the last slide, we need to find a common denominator. Well, the LCD for the numerator is x plus 1. Since the first term already has that, I'm just going to keep x plus 3, but I'm going to take the negative 2 times x plus 1. Again, don't forget that's all over x minus 1. All right, I'm going to combine some like terms in the numerator. Well, actually, let's distribute the negative 2 first, because sometimes if we combine too many steps, we make mistakes. So remember that the negative goes to both terms in the parentheses. Okay, now I'm going to go ahead and combine like terms. So my numerator is going to become negative x plus 1, if I combine the x's and the constants, over x plus 1. And then just like in the last problem, when we divide the numerator, that fraction on top, by x minus 1, it's the same as multiplying by 1 over x minus 1. So I'm going to change it to a multiplication problem. Now, wouldn't it be nice if this numerator right here, this first numerator, would look like this denominator or this denominator so that I could reduce? Well, I notice it doesn't look like the first one because it has a negative in front of the x, and it doesn't look like the second one because the negative is not in front of the x, but it's in front of the 1. Well, I recognize that in the first fraction, I can factor out a negative 1. And if I factor out a negative 1, it becomes x minus 1. And now it is the same as the second denominator. Since this is now the same as my numerator, as one of the factors of the numerator, I can reduce, getting me an equation of negative 1 over x plus 1. So this would be my difference quotient, my finalized difference quotient between the point 1, 2 and any other point on the line. So you might say, okay, so what does this get me? Well, remember in the previous slide, we said that we wanted to know between the point 1, 2 and 5 4/3. And we found that slope to be negative 1/6 on the previous slide. All right, well, instead of needing the whole point now, if I use this formula, I just simply need to replace the x value with this x, because I already have 1 in it. I already have 1 and 2 in it. This point's already in it. That's how we wrote this. So I just have to put the 5 in. So it'd be 5 plus 1, which would be equal to negative 1/6. So we get the same answer. And the nice thing is, after doing this once, now if I wanted to find the slope between the point 1, 2 and say 10 and its corresponding y value, I can just plug in 10 and I know it would be negative 1 over 11. Another difference quotient that we use a lot of times in calculus is the one that you see here. Now, this difference quotient also is a slope formula. The difference is on this one. We say that we have the point A, comma, f of A. And then instead of stating the second point, we just say how far away from A we want the x value to be, the second x value to be. So we say that we have A, but then we're going to move h units away from A. So then its corresponding y value would be A plus h. So let me give you an example here. For example, let's say that I want to find the rate of change for a equals 2, and then change in the x values of 1. So that would mean that my first point would be the point 2, comma, and then the corresponding y value. To find the corresponding y value, we plug 2 in for x into this equation. So we would have 8 minus 10 plus 1. So we'd have negative 1. And then to find our corresponding value for a plus h, which a plus h in this case would be 2 plus 1, comma, f of 2 plus 1. So we would have 2 plus 1, which is 3. And so again, if we go plug 3 into this equation, we would have 2 times 9, which is 18, minus 5 times 3, which is 15, plus 1. So we would get 4. Now using our good old-fashioned generic slope formula, we would get 4 minus a negative 1 and 3 minus 2, which will end up being 5 over 1, or 5. Now, that would be then this point here, 2, negative 1, and 3, 4. So we are finding the rate of change or the slope between those 2 points. Now, you might say, well, if we just use the good old slope formula using these original equations that we came up with, or these original points, how do we get just h in the denominator? Well, if it's y minus y, I'm going to have this y, which is f of a plus h, so that's y2 minus y1. And then I would have x2, a plus h, minus x1, a. And if you notice, the a's will cancel out. And that is how we get to this formula. So I want you to remember again that starting at a equals 2 and moving a distance of 1 away from a to the right, I ended up with a slope of 5. Now we're going to take a look at how we do this algebraically. Oftentimes when I do these algebraically, I like to break up each part. So I like to find f of a plus h first, f of a, and then put it all into my equation. So I would have f of a plus h. Well, I know that f of a plus h is going to equal this f of x. Instead of writing x, everywhere there's an x, I'm going to replace it with an a plus h. So I have 2 times x squared minus 5 times x plus 1. And again, I'm going to replace those x's with a plus h. So that's how the equation changes. That's what that functional notation does for us. Alrighty, so now I need to simplify this. I'm going to have 2 times, and if I go ahead and I know this is a perfect square, so it's going to be a squared plus 2ah plus h squared minus 5 times a, and don't forget to distribute the negative sign with the 5. All right, so I'm going to simplify just a little bit further here, and I'd have 2a squared plus 4ah plus 2h squared minus 5a minus 5h plus 1. Okay, and that's just f of a. Now I need to, or f of a plus h. Now I need to find f of a. Well, f of a is just going to take that original equation, and everywhere that I have an x, I'm going to go ahead and replace it with an a. So this one won't have as much reducing to do. So I'll have 2a squared minus 5a plus 1. All right, now I'm ready to put that all into my equation and simplify. So f of a plus h is our first term. Well, here's our f of a plus h right here. So I'm going to bring that down here, and it's going to be 2a squared plus 4ah plus 2h squared minus 5a minus 5h plus 1. So that's just f of a plus h. Now I'm going to subtract from that f of a. So I have 2a squared minus 5a plus 1. And I'm going to put that all over h. And again, that's kind of a common thing that we forget to do. So don't forget to do that. Now, I'm going to go ahead and I'm going to distribute this negative symbol to everything in the parentheses back here. So I'm going to make it a plus, but then I'm going to make each one of these their opposite. That's another common error. In doing that, you'll see that 2a squared here with minus 2a squared here cancels. Negative 5a and positive 5a cancel. And I have this plus 1 and this minus 1. And I'm telling you right now, this will always cancel out. If it doesn't, that thing that you're subtracting off, then somehow in there we've done our math wrong. Because at this point, we should only have h's left in the numerator. With that being said, since I have this h here, I have two h's here, and an h here, I'm going to go ahead and factor that h out front. So I'm going to bring that h out front, leaving me with 4a for the first term, 2 h's for the second term, and a minus 5 for the last term. Now that's still all over h. Now that I factor that h out, I can go ahead and reduce, getting me a generic equation, and this is just a slope equation for any starting x value and any distance from that x value. Now, I told you to remember what we did on the last page, the last slide. We said that a equaled 2, and we went a distance away from 2 in the positive direction of 1. So if I go ahead and plug that in here, I would get 4 times 2 plus 2 times 1 minus 5. So I have 8 plus 2 minus 5, or 10 minus 5 for 5. And if you recall on the last slide, it's exactly what we got for the slope, from a equals 2 and having a distance of 1 away from it.